I'm basing this talk, I've sort of built a story out of a few papers. A paper I had in ESOP, a paper we had in LICS, and a paper that just appeared, no, it's appearing this afternoon in POPL. So if you want to know more, you can have a look at those. On the one hand, and I think we've seen things across this spectrum over the last couple of days. On the one hand, you might have handwritten statistical models and inference methods. Maybe a statistician, a very clever one, has sat down and fine-tuned a very good R package. Loads of people use it, but it just has a few parameters for tweaking it. Then you might go to some sort of thing like bugs or something like that, where you've got, again, a very good inference algorithm, a good interface to it, but given by a much more powerful system, but a restricted language nonetheless. And then I'd like to go all the way and see how far we can go towards general purpose languages, but with probabilistic constructions. And then this idea, I think that Peter mentioned at the beginning of the talk, of separating the model from the inference algorithm. So here the model is tied to the inference algorithm, but over here we can try as much as possible to separate the model from the inference algorithm and plug in different inference algorithms. And we can understand then what is a statistical model as a separate question from what is an inference algorithm. So Anglican's a language developed in Oxford, but there's lots and lots of other languages out. Okay. So yeah, so let me start with a few words of motivation. What is a semantic foundation for probabilistic programming? We're talking about logic. Then what is the underlying logical formalism for understanding probabilistic programming? And why is that an important question? Well, because it's a lovely question, but also because it helps us answer some questions. And one question is, what's the landscape of expressivity of languages? I think once we understand a semantic foundation as opposed to sort of a BNF grammar of languages, we can sort of see how to go right across through to ultraviolet perhaps, or where we want to sit, where's the sweet spot where things are working well. And what I want to show you at the end of this talk is how to understand validity of inference algorithms. If we're going to have a general purpose language where we can run different inference algorithms on it, what does it mean to say those inference algorithms are correct or converge or whatever? And finally, sort of validity of probabilistic programs. And that might be in a traditional sense of programming language theory, checking that programs satisfy a specification, but it might also be in a statistical sense. So if you open Ghahramani's book, is it called Bayesian Data Analysis, there's a chapter called model checking. So you might think, oh great, we're logicians, we know about model checking, but it's a totally different kind of model checking. It means checking that the statistical models are not too sensitive to the various aspects of the data or of the models themselves. Okay, so I'd like to be interested to be able to understand that. So that's done kind of informally typically. It'd be interesting to put that on a kind of a formal footing. So the talk will go something like this. I'll start by illustrating some of the key ideas. I'll spend about half the talk doing that, fairly high level, and then I'll go down to some more detailed stuff, right down to some new foundations for measure theory, and then build up to a valid collection of modular inference algorithms. And at the very end, I'll say a couple of words about some other directions. Okay, so let's start with a simple example just to set the scene of what I mean by probabilistic programming. So Bayes' law, we've seen several times, and hopefully you all know. Bayes' law says the posterior is proportional to the likelihood times the prior. So we've got some data which gives us some likelihood, and we multiply that by some prior knowledge to get a posterior belief. So everything I'm going to talk about today is Bayesian. Probabilistic programming then for me is sequential programming, and you can vary what you mean by that, plus a new construction for every clause in Bayes' law. So there's something called sample, which draws something from a prior. There's something called observe, which records the likelihood of some data. And there's something called normalize, because the posterior is not equal to the product of the likelihood and the prior. It's proportional, so we need to find the normalizing constant. So I'm going to add those three constructions to a programming language. So here's a little example. I tried various stories when I've been explaining probabilistic programming to people, and this is a story I found tends to work quite well, so let's see. It's a kind of a high school statistics simple story. A call center operator doesn't know what day it is. He does know the rate of calls, so he knows at weekends you get 3 calls per hour, but on weekdays you get 10 calls per hour, so people tend to phone up while they're at work, I suppose. And then he notices a 15-minute gap between calls, and he wants to answer the question, is it the weekend? So I guess he's got a watch, but the watch doesn't tell him what day it is. Okay. So that's an informal description, and with such a short thing, you could go away and just calculate it on the back of an envelope. But let's write it down precisely. So to write down precisely, I'm going to use probabilistic programming language. So we want to normalize, we want to find a posterior for the following story. Let the weekend be a Bernoulli distributed, so it's 2/7, let's say that we uniformly don't know which day of the week it is, so 2 days of the week are weekend days, so we toss a biased coin and say 2/7 of the time it's the weekend. That's our prior. Then we let the rate be either 3 or 10, depending on whether it's the weekend. And then we observe a quarter of an hour gap between calls. Now, calls coming into a call center, we could say a Poisson, form a Poisson process. So the gap between them is exponentially distributed with the rate being either 3 calls an hour or 10 calls an hour, depending on whether it's the weekend. So that describes formally this informal description at the top of the slide. Okay, just if you can't remember the exponential distribution, this is the density function of the exponential distribution, and you can see that when the rate is 3, then the density is just above 1, and when the rate is 10, then the density is just below 1. The likelihood, if you like, is just below 1. Something else I wanted to say. Oh, yes. So in the previous talk, the observations were all hard. We say hard, they were hard constraints. We were rejecting anything which violated those constraints. Here is what's called a soft constraint, because we're not saying that 0.25 is equal to, so this is not a Boolean clause. This is saying that we drew 0.5, or we observed 0.25 coming from a distribution. So I'll explain what that means in a minute. The other thing to say is that although the areas under these curves are 1, the probability density functions, the values can be above 1 or below 1 or whatever. Okay. So that's probabilistic programming. Right, we add these 3 constructs to a normal programming language. Let me talk about understanding semantically what's going on in probabilistic programming. So in that example, and in probabilistic programming, we have these 3 extra features: sample, observe, and normalize. So I'm going to give an informal semantics. If you want to see a more precise thing, you can look in my ESOP paper, or roughly it's based on Dexter Cozen's work, I suppose. So if I say let X be sample, and then I continue with K, what does that mean? Informally, let me first say, the meaning of a program is a measure. So that might be a probability measure, but typically it's an unnormalized measure. And it's a measure on the type of the stuff that we're talking about. So if it's a real-valued program, it's a measure on the reals. If it's a Boolean-valued program, it's a measure on the 2-point space. So if the rest of the program is a measure, kx, then when I say let x be sample mu, so I'm drawing from a prior, this is mu is a probability measure, that means integrate the rest of the program, kx, the measure, with respect to mu, the probability measure. When I say observe x from mu and then continue as k, that means, remember, k is a measure describing the rest of the program. It means multiply that measure by the density function, by the likelihood of the data point coming from that distribution. And when I say normalize, if I think of the rest of the program as being a measure, it just means take that unnormalized posterior, that unnormalized measure, and divide it by a normalizing constant, which is the measure of the whole space. That's quite an expensive thing to calculate, obviously. So just normally you only integrate real-valued functions. Here these are measure-valued functions, but it doesn't matter. So just coming back to this example, we can calculate precisely, because it's such a simple example, the unnormalized posterior. So the unnormalized posterior, that it's the weekend equals true, is 2/7, because that's the prior, times 1.42, which is the likelihood, which gives us 0.405. The unnormalized posterior that it's a weekday is 5/7, which is the prior, times 0.82, that's the likelihood, that's the point where 15 minutes hits the density function of that purple curve, which is 0.586. Now together these numbers don't add up to 1. This is an unnormalized posterior. And so we normalize it by dividing by their sum, by the normalizing constant. And this gives us 0.408. Okay. So the posterior probability of it being the weekend is 0.408. So it's still probable that it's a weekday, but it's less probable than our prior was. Okay. Just to show that things can get more interesting than just that very simple example. Suppose he doesn't know what time it is rather than what day it is, and he knows the rate of calls, how that changes with time. You could describe that rather than by drawing from a Bernoulli distribution, sampling from a uniform distribution across the whole of the interval between 0 and 24. And then when you do calculate what the measure is going to be, you're going to be integrating over that interval. Right, so that's a summary of, informally, what the measure theoretic semantics of probabilistic programs looks like. But how do we actually run them? Okay. So how do we run probabilistic programs? The very simplest idea is to do a Monte Carlo simulation. A Monte Carlo simulation means you run the program many times. Each time you're going to get a result, true or false in the case of the simple story. But you're also going to gather an importance weight. So as you run through the program, you multiply your weight as you go by the likelihoods of the data that you see. So actually, in practice, what you would use would be a log likelihood, so you would add together these weights. But yeah, we keep track of that weight. And so at the very end of each trace, we run the program many times, we end up with a likelihood weight and a result. And the normalization constant then, if we run it 1,000 times or 10,000 times, is the average weight across all of those traces. So in this simple example, there's only two possible ways. You could run the program as many times as you like, but you'd only ever run through it in two possible ways because there's only one Bernoulli trial here. And one way you would get it being the weekend, and the weight would be 1.42, which is the likelihood of a call coming in after a quarter of an hour when the rate is 3 calls per hour. And the other one, you would get the weekend being false, and the weight of that would be 0.82. And so you put those together to find a posterior. So that's a Monte Carlo simulation, but it's a very naive thing to do. Some concerns, right? So let me say first that looking at this program, it's very short. One popular probabilistic programming language, Stan, which is used by thousands of people. That's just to give an idea of what sort of things you might do with them. It's sponsored by YouGov, amongst other people. So there you would have a model of voter behavior. Right, so that's going to be more than 4 lines long. They were able to predict the UK general election quite accurately, actually. So, right, so the program might be actually very long with lots and lots of data, lots and lots of random inputs. So what can you do? Well, you're spending too much time on the traces that have low weights. Right? If you had particularly chose a prior that ended up having not matching the data very well, that trace would have a low weight. And you don't really want to then carry on running it for the whole of the rest of the 1,000 lines of the program. So one way to deal with that is sequential Monte Carlo simulation. And I think it has a very nice description in probabilistic programming. I'm going to talk about it again towards the end, so let me summarize it. Sequential Monte Carlo simulation from the point of view of probabilistic programming means every now and then you pause, sort of a checkpoint, you pause, you resample, you calculate a posterior, you resample from that, and then you carry on. And that ensures that you don't have too many traces with low weights. Another technique, another issue is that if you've got lots and lots of sample statements, you're drawing from lots of different distributions, that makes it very costly if you're doing that 10,000 times. So why not try and avoid resampling from distributions every single time you run a trace? And so, to me, Monte Carlo Markov chain methods, Metropolis Hastings methods say the following from the probabilistic program perspective. Rather than every time you run through a program resampling every time, why not reuse some of the samples in a careful way? Okay. So those are some aspects of probabilistic programming at a glance. Let me say a bit about pushing beyond that simple kind of probabilistic programming towards higher order functions. So I want to talk about Bayesian regression. So regression problems are about fitting lines or functions to some data points. A Bayesian regression, remember, says not just what's the best fit, what's the least squares line or something like that, but what's the distribution over, what's the posterior distribution over lines that fit these data points. Okay, so here's some data points, and here this is going to be the posterior when we run our inference algorithm. So it's a distribution where you can see what the mean is, but you can also see how the standard deviation or the variance looks like. Okay, so here's a model written as a probabilistic program for doing Bayesian linear regression. There's a mistake here, see if you can spot it while I'm talking through. So the prior says we've got a slope and a base. A linear function is determined by two coefficients. And then we define f to be a function that takes an argument x and then returns sx plus b. So f is something where we don't really know. The standard deviations here are pretty big. We don't really know where this line is going. And then we observe that f0 is 0.6, f1 is 0.7, and so on through to f6 is 8.4. And then we want to find a posterior distribution for this kind of line. Anyone spot a mistake with this model, why it wouldn't work? Oh, every time somebody's found a mistake. Anybody? Okay, so what I've written here is that I'm observing that as a sort of a hard constraint, that 0.6 is exactly the value of the function f at 0. But actually there's no line that would perfectly satisfy all of these 7 constraints. They're not collinear, the points are not collinear. So what must have happened was we didn't actually look at the precise value of f0, but we measured it noisily. We had, our measurement tool was a bit faulty, or eyesight wasn't very good, or something like that. So what you would typically do, the very simple thing to do to deal with that in Bayesian linear regression, is to say, actually we didn't observe f0, we observed something that was drawn from a normal distribution with mean f0, but with a standard deviation of 0.5. That's quite a big standard deviation, so it was a bit of a noisy measurement. And similarly with f1 through to f6. We didn't observe their actual values, we just observed a noisy measurement of their actual values. So something normally distributed about those points. And you can make a more fancy model, because maybe you don't know what the standard deviation should be. So you could also draw that in your prior, right? And maybe the measurements were made by different people. Some of them are more clumsy than others. So then you should draw 7 different standard deviations. Okay, so just to give you a picture of what's going on. Yeah?
In which sense was that a mistake before?
It's a bad model. There'll be no solution. There'll be no solutions to this model.
But it has semantics, or
it has semantics as a. But okay. So when I say normalize can fail. Can fail for 2 reasons. One is that the normalizing constant is 0, which is what's true in this case, and the other is that the normalizing constant is infinity. Yeah, good question. Any more questions just now? All right, so just to cut away the observations, this is what the prior looks like. You see it's not a uniform distribution over lines, because that would be impossible, but it's a fairly uninformative prior. I generated these using Anglican, by the way. And this is what the posterior looks like. Okay, so the problem is, what is f? This works well in Anglican, as I said, you just run it and it works. What is f in terms of statistics, in terms of measure theory? A problem is that measure theory doesn't actually support higher order functions. So Aumann is a Nobel Prize winning economist, but over 50 years ago he showed that the evaluation function that takes a function and an argument and produces the result is never measurable, no matter which sigma algebra you choose on the space of measurable functions. So there's no way of supporting fully higher order functions. There are things you can do, and everybody knows lots of tricks, right? But you cannot fully support higher order functions. But higher order functions are really useful. So let me push this a bit further. So here's that program that we saw. I'm just going to change it a little bit. I'm going to put this higher order function piecewise on top of the prior. So piecewise, I won't show you the definition, but it takes a random function and produces a new random function, which is piecewise bits of the first random function. So if I gave it if I gave a linear random function, piecewise will produce a piecewise linear function. If I gave it a constant random function, piecewise would produce a piecewise constant function and piecewise polynomial and so on. So piecewise is a higher order function that takes a random function and produces another one. And so we can again ask Anglican to find a posterior when we've just added in this higher order function piecewise, and this is what it does. So it's fitted some piecewise linear functions to the points. Right, so this illustrates a little point about probabilistic programming, I think. So I did this very quickly. I just chucked the word piecewise in. And I've got no idea why Anglican's clumping things together like this into these little bits. So you can very quickly prototype things, but maybe you need to fine-tune to get things to work well. So there's no utopia. You've still got to do some hard work if you want to get really good, complicated models, I think. Okay, so that's what I wanted to say to sort of motivate higher order functions. Oh, let me also say that, yeah, you could change the prior even more. We could put polynomials here. We could maybe put a Gaussian process here. We could maybe even put a distribution over programs, so that now f is ranging over programs. We don't change the rest of the probabilistic program at all. Now we're trying to fit some programs to some models. I can show you that later if you like. And that'll be program induction, I suppose. Okay, so that's a kind of a first introduction to the first part of the talk. So a high-level idea of the kinds of things that we might be able to deal with semantic foundations. Okay, so now what I want to do is to go into some technical detail. I'm going to jump right down and talk about new foundations for measure theory, because I think we need them. And then I'm going to build up towards some new modular valid inference algorithms. Just to sort of show you where we're going before I go down into the exciting technical stuff. Remember what we said about these different solutions to naive Monte Carlo simulation being inefficient, and our take on this is in our paper in POPL, is that modular inference, exact inference is intractable. What you'd like to do is use the true mathematical semantics, but you can't do that because it's uncountable, to say the least. Right. So what we do instead is to have some program representation, some software representation of that true mathematical semantics. And you could start with a naive one, but then you use some transformations to move to a more elaborate one. And so some of those transformations will be introducing Markov chain Monte Carlo simulations. Some of those transformations will be introducing the kinds of things in sequential Monte Carlo simulations. And you can then start to combine them to get things like resample move, sequential Monte Carlo methods. Okay. But to understand this, I want to explain to you what the true mathematical semantics is, I suppose. Okay. So this little part is going to go in 3 steps. I'm going to first talk about what I'm calling a synthetic measure theory. Then I'll show you our new model, which is quasi-Borel spaces. And then we'll come back to the practical stuff. Okay, so what do I mean by a synthetic measure theory? Well, first let's ask, what's a mathematical universe of probabilistic programming? We've seen that we've got all kinds of probability measures and higher order functions. I think the same sort of question is, what's a synthetic measure theory? If we could build a measure theory that had all the properties that we wanted, what would it be? So we're inspired by this, by the work of Anders Koch, who spent many years developing a synthetic differential geometry, and recently had this paper, quite a simple paper really, on a sort of a synthetic theory of distributions. So we've been looking at that and then trying to build a model of it. Okay. So let me talk about what sort of things we would want. We want higher order functions, or I don't speak for all of us, I want higher order functions, and I guess natural numbers at least. Higher order functions because they give us compositionality, they give us modularity, and they give us sort of some aspects of higher order logic. So formally, we need a Cartesian closed category with sums. We want for every space, X, we want to be able to talk about the measures on that space. And because we want this whole thing to be first class, we want to also have that set of measures to be a space itself, and to be able to integrate with respect to it and so on. So what Koch noticed is, or maybe other people noticed it before, what you need is so-called commutative monad. And finally, the third criterion is we want M1, the measures on the one-point space, to behave like the extended positive reals. Because if you've got in traditional measure theory, if you've got a one-point space, what's a measure on it? It's just the size, the measure that you give to that single point. And Koch noticed that these 2 axioms, or slight countable generalization of that one, are enough to guarantee this. So the first one says the measure on the empty set, so there's only one measure on the empty space, which doesn't need to say anything. And the other one says if I've got a measure on disjoint union of spaces, it's the same as giving a measure on the 2 spaces separately. And these axioms are enough to make sure we have a semi-ring as M1. Okay, so that's a kind of axiomatic account of what we would like. And the reason I say it's the same question as what's a mathematical universe for probabilistic programming is because you can move backwards and forwards from measure theoretic notation to programming language notation. So rather than using the sort of the let language I was using before, here's a kind of a Haskell type notation on the right, and on the left we've got measure theoretic notation. I'm sorry, that should be 0 to infinity. And so as I said already, 0 to infinity, the interval should be measures on 1. And then we can talk about push-forward measures. Dirac measures is the return of the monad. Integration, as I said, is sequencing. Remember I said the meaning of sequencing in a probabilistic programming is integration. So we can just write an integral symbol formally for that. Product measures we can talk about, expectations we can talk about, and so on. So what we found was we wanted to prove some theorems about our new model, which is quasi-Borel spaces, and we found that we could go from looking at those theorems in the literature, understanding what they meant with integration, and then just rewriting them formally, and then translating them into probabilistic programs or into the model, which is quasi-Borel spaces. Okay. There's a problem here, which is that classical measure theory is not a model of what I've been calling synthetic measure theory. Why is that? Because classical measure theory doesn't support higher order functions, because I very strongly believe, but I haven't got a counterexample, classical measure theory doesn't support having a commutative monad of measures. You can't build a space of measures in classical measure theory. So something needs to be done. And so I'm going to do it. Or I've done it, I suppose. Okay, so now I'm going to introduce quasi-Borel spaces, which is my new, our new model of measure theory. So what we want to do, right, measure theory works perfectly well for first-order languages. Everything works fine. So we don't want to tamper with that. We want to be conservative about keeping that the same. So normal statistics, as it works with first-order stuff, should be fine. And we want to embed it into a bigger class of spaces that does deal with higher-order stuff. And there should be some conservativity theorems, and there is going to be an adequacy theorem. So what is classical measure theory? Well, the place where it works best with disintegration theorems, Finetti theorems and so on, is in standard Borel spaces. These are spaces like the reals, the natural numbers, sequences of reals. Most of the spaces that you would use are standard Borel spaces. And what's the bigger class of spaces? It's going to be quasi-Borel spaces.
Sam?
Yeah.
So we do know monads on standard Borel spaces, so why don't we like them?
Right, they don't satisfy those conditions I showed you.
So they're not commutative?
They are, maybe you can tell me later. But certainly the Jury monad doesn't satisfy the other conditions about additivity. Yeah. Right, so this is a monad of all measures, not of probability measures. And you can cut down then to probability if you want to do that. But I think I showed you in the beginning example, you want to be able to talk about unnormalized measures when you're talking about probability. Okay. Right. So the basic slogan, if you want to remember what quasi-Borel spaces are, is that random elements come first. If you talk to a probability theorist about measure theory, they'll say, yes, we do have a foundation of sigma algebras and measurable functions, but actually what we care about are the random elements, the random variables. And so in quasi-Borel spaces, we put those at the center of the story. So what is a random element? What's a random variable? Let's remind everybody. So in probability theory, you usually say there's some global sample space. Maybe you never actually know what it is, but it's there. It's maybe the state of the whole universe. It's maybe a collection of random seeds. And all you ever actually look at are random variables or random elements, which are sort of projections or functions out of omega, out of the sample space to X, to some space of values that you want to look at. Often it's the reals, but it might not be. What I'm going to do is to assume that omega, my sample space, is the reals. So because the reals are isomorphic to sequences of reals and so many other spaces, it doesn't really matter. Yep.
Does this quasi-Borel space support for discrete, or is this?
No, absolutely, absolutely. Yep, yep. So X could be. I said the sample space is going to be the reals. I'm going to fix that, but X could be the set with two elements. Okay, so here's the definition. I think it's a very simple definition. A quasi-Borel space is a pair of a set together with a set of functions. And the idea is these functions are going to be the admissible random variables. We don't allow all the functions from the sample space R to X as random elements, but we cut down to an admissible set. And so a quasi-Borel space is a pair of the set and this set M of admissible random elements. Now, any mathematical definition comes with some conditions, so here are the conditions. It should satisfy these three conditions. The first condition says that sort of the Borel structure of the reals is respected. So if f is a Borel measurable function from reals to reals, if you don't know what that means, it means it sort of supports integration nicely. And then we have a random element that's a function from R to X, then we should be able to compose those two things to get another random element. The second condition is, it's long when you write it down, so let me try and explain it with my hands. If I take the reals, I can divide it into a countable collection of Borel sets, maybe just the evens and the odds or something like that. And then I could use a different random element for, depending on whether I'm, let's say, in the evens or in the odds. So I've got these alpha 1, alpha 2, all these different random variables, and then I've split the reals into a countable number of pieces. I can then patch those up into a combination, and that should again be an admissible random element. So my admissible random element should be closed under these two conditions. It sort of gives you a countable case split. And finally, the last criterion is that all the constant functions should be allowed. So that means that we can always talk about a particular element non-randomly of our quasi-Borel space X. Whenever you've got a mathematical structure, you should tell people what the morphisms are, what the right kinds of maps between the spaces are. So a morphism from one quasi-Borel space to another is just a function, because a quasi-Borel space is a set together with some structure, and it's a function that preserves the structure in the only obvious way, that if we compose it with random elements, we get new random elements. Now, for example, a crucial fundamental example is this. If you start with a measurable space, particularly a standard Borel one, then you can take all the measurable functions. Those are what you would normally call the random variables or the random elements. And you can then form a quasi-Borel space. So given a measurable space, you can always form a quasi-Borel space by taking the measurable functions as M. And then if you look at what the definition of morphism means and just go through a few lines, you find out that morphisms and measurable functions in the classical sense are exactly the same. So we've got inside quasi-Borel spaces all of the standard machinery of classical measure theory. Okay. So quasi-Borel spaces include standard Borel spaces fully faithfully, but there's more in there than just the standard Borel spaces, than just the measurable spaces. Because if we take the set of morphisms between any two quasi-Borel spaces, we can easily make that into a quasi-Borel space again. So we can form spaces of functions. We have higher order functions inside this model. So those criteria for synthetic measure theory, the first one is satisfied. Now let me talk about the second two briefly. We have higher order functions. So a quasi-Borel space is a set together with a collection of random elements, admissible random elements. What's a measure? So the other criteria, by the way, we need to be able to talk about measures. So a measure on a quasi-Borel space is just defined, as a probabilist would define it, to be a measure on your sample space, on omega, or on your collection of seeds, together with a random element, an admissible random element, and a random element coming from M. So a function from the reals, that's our omega, our sample space, to X. Now, whenever you've got a measure on a quasi-Borel space defined in this way, you can define a notion of integration. So if I've got a quasi-Borel morphism from a quasi-Borel space to the reals, and a measure on the space, then I can always integrate the function, find the expected value of the function with respect to the measure, and that's very straightforward to write down. And so what we can then say is two measures should be the same if they induce the same integration operator. Measure and integration should go hand in hand. So that's what a measure is, and it's quite straightforward also to turn the collection of measures in this sense into a quasi-Borel space itself, and then to show that we get these conditions satisfied, that we have a commutative monad, and the measures on the one-point space are exactly 0 to infinity. Let me say a couple of words about that. So what we can always do, actually, rather than asking for a sigma finite measure on the reals, is to say there's a randomization theorem which says it's enough to talk about a Lebesgue measure on a subset of the reals. Okay, so now we can come back and ask, actually, so now we've got these higher order functions living inside quasi-Borel spaces. What are measures on those? So remember, a measure is defined to be a measure on the reals together with a function from the reals to the space. But a function from the reals to the space of functions from x to y, we can curry that and talk about a measurable function from the reals times x to y. And these are exactly what probabilists call random functions. So random functions, usually if you look in a probability textbook, are defined separately from random variables. But here we see they're both instances of the same concept, which is the notion of a measure on a quasi-Borel space. So I thought that was quite nice. For example, the piecewise higher order function that we talked about at the beginning takes a random function, for example, a random linear function, and produces a new random function which is piecewise like that function that we started with, that random function that we started with. Okay, so this is a genuinely higher order function. Okay, let's come back also to look at that example with linear regression. Let me just look at the prior, because that's a bit simpler than the whole thing. What does the prior look like as a measure on a space? So remember, a measure needs to be a pair of a measure on the sample space together with a random function, a measurable function. And in this example, let's notice that the reals are isomorphic to the plane. And then let's let mu be, well, we need to somehow have both of these S and B in there, so let's have a multivariate normal with the mean being the origin of the plane, the center of the plane. And then our measurable function has to take a seed, and something coming from this sample space, which is a pair of it's two things because we're working up to this isomorphism. So that's a pair of an S and a B and an X, and it's going to produce Sx plus B, which is the linear function that we were talking about. So that's what the prior looks like as a formal, precise, logical object. Okay, let me talk a bit then about modular and valid inference algorithms. So now that we know where we can understand measure theory and probability theory as living, we can understand this picture perhaps a bit better. Let me just emphasize what kinds of things you might have here. So here's a very simple intermediate representation that we might start with. It's extremely useful. Let's take a probabilistic program, which is a model, and let's forget about observes for a minute. So we've just got some samples, maybe from continuous distributions. Let's turn it into an uncountably branching tree, where every time we see a sample statement, sampling from a prior, we introduce an uncountable number of branching across all of, let's say, 0, 1, where you can use that as our sample space, and then we carry on. So it's an uncountably branching tree. It looks hideous, but in Haskell, you can quickly, laziness lets you do all sorts of things. But manipulations of this structure, if we want to understand them precisely, are higher order functions. They're functions that take functions or things more complicated than that to other structures. And what we showed is various things, but in particular, I think the hardest thing was to show that the Metropolis-Hastings-Green algorithm for Markov chain Monte Carlo simulation works not just in standard Borel spaces, but in quasi-Borel spaces. We did that, as I said, by understanding how it works classically and then translating via synthetic measure theory, sort of being able to use the standard notation makes it very easy to copy the proof across. So before I show you that, so this is the sort of the end of our paper in POPL. But then Adam Ścibior, who is a PhD student, had implemented a Haskell library, so he was going to write a paper about that implementation. I said, if you're going to write a paper, you better run some benchmarks. So it's hard to benchmark these things because there aren't many benchmarks around, I think. But he was really, he said, it's never going to work well because we've done it in a verified way, we've done it carefully. I've just done it really quickly and naively and in a modular way as well. It's never going to work well. So we convinced him to run some benchmarks. And we were really surprised that actually his library, so it says ours, it should be his. Right? His library works better, at least in these examples, than Anglican and Web people. Okay? Not by by any big factor, but still it's not performing badly at all. So you can have modular stuff, you can have valid, proven correct stuff that works efficiently, it seems. So I must say, that's not my work, right? But Adam just showed me those before I came. So you can wait for that paper to come out. Okay, so that's sort of the core of what I wanted to say. If I could have one more minute, let me say, I want to have a different direction, because where we could go involving logic. And so when I talked about synthetic measure theory, one of the axioms was commutativity. I said we must have a commutative monad. I didn't say what that meant, so let me say what that means. In terms of programs, it means that we can reorder the lines of a program. That's really useful in program analysis and so on. It means we can just think about, rather than a control flow diagram, a data flow diagram. So here I've sort of drawn these programs as diagrams. Now you see they look a little bit like graphical models, something like that. From the synthetic measure theory point of view, it means we can do Fubini's theorem. We can reorder integrals. Okay. What the language Church, so Church was a language developed at MIT maybe 10 years ago now. On top of the usual probabilistic programming stuff, they allowed you to add exchangeable random primitives. These were things like memoization, generating symbols, gensim, Dirichlet processes combined with memoization, and so on. And one thing that they say, this is just it's just an implementation. I don't think they formally worked out what was going on, but they said you should be able to still, when you introduce new exchangeable random primitives, you should still be able to do these kinds of reorderings. So memoization in particular, you can, although it's a stateful thing, you can still reorder the lines. Even though they do different things when you reorder the lines, they behave in the same way. And what I wonder is then if perhaps these are new models of synthetic measure theory. So one aspect perhaps of logic applied to data science that's not represented here is work that began, I think, in the 70s and 80s on using non-standard analysis to study probability theory. And out of that came some beautiful techniques in Bayesian non-parametrics like graph funds. And so I wonder whether, and so they're very widely used now, not that non-standard analysis is widely used by data scientists, but those techniques can be widely used. And so I wonder whether this kind of line of synthetic measure theory could also propose new ideas in Bayesian non-parametrics. Okay, thanks.